All right. All right. I'm feeling lucky. What do you got?
A straight.
You can't keep doing that to me. How do you... Tip of the day, don't play cards with a mathematician, because despite what you might think, they can be experts on randomness, as is Magnus Bordewich. Hey, thanks for talking to us today, Magnus.
No problem.
Now, what area of random maths are you into?
Well, I'm interested in sampling from probability distributions, but in particular ones that are hard to compute. So we have some sort of iterative process, very like shuffling a deck of cards, in which the more you shuffle and the more you iterate this process, the closer to random the thing we're sampling becomes.
I guess there's got to be a stage where you say you've got to put a full stop and say, well, we've got to stop shuffling sometime.
That's right, yeah. The setup is typically that if you were to keep going forever and ever and ever, you would end up with a truly random sample. And if you keep shuffling a deck of cards forever and ever, you get a really well shuffled deck. But most people stop after a few shuffles because they accept that's close enough to random. And we have to do the same. We measure the difference between two probability distributions, and we try to capture how long we have to wait for that difference to be small enough for whatever use we're making with the data.
So what sort of areas of practical application could you use this type of maths for?
So one of the key areas is statistical physics. So here you're dealing with something like a model of a large piece of iron, where what we understand are the very small scale atomic structure. So it's made of a very large number of atoms that interact with their neighbors. They're kind of like very small atomic magnets that want to align with their neighbors. And we need to sample the state of the whole block of iron. Now, there are too many atoms and too many possible configurations to do the whole thing straightforward calculation, but using an iterative process to do with flipping all the little atomic magnets, we can approach a random sample from this distribution.
So why would you want to model the molecules in the iron?
The situation with tempering steel is actually used algorithmically in other areas, and we call it simulated annealing. And the idea is, at high temperature, the magnets are very free to switch, so you quickly approach a random situation. Whereas at cool temperature, which may be where you're interested, they're not free to switch, so it takes a long time to reach the required distribution. And what you do algorithmically is set your temperature parameter high, it mixes fast, and then you slowly cool your distribution or your chunk of iron, and it cools from a well-mixed state into something which is random in the cold setting you're interested in.
Okay, all right. So does this area of maths also cross into another area of your research which involves looking at endangered species and deciding how to apply limited resources to them? Do we decide to save the duck or the dinosaur type of thing?
It is. You're talking there about the nature reserve selection problem, and this is one where you have some number of potential nature reserves, maybe 50 or 100 local areas that have been identified, and you want to choose maybe 10 or 15 to fund. And you want to know which is the best choice of 10 or 15 nature reserves to fund to conserve a good biodiverse set. Now, with numbers like that, choosing any possible 10 from 100, there are too many choices that could be made for you to evaluate every single one. So you need some structured process to go through and zoom in on the ones that are good. And this is algorithms. This is the same sort of process as sampling from a random distribution, but now we don't want a random one, we want one with a high biodiversity score. But you need a structured process to get there, and that is the study of algorithms.
Oh, well, with all that in mind, maybe we could try playing another game of cards I know. Have you heard of Snap?
I have.
Well, I reckon I might have better chance at beating you with Snap. Now, so, okay, you pick those up. Are you going to iterate the deck or shall I?
Go ahead.
I think it's about time I iterate. I don't know if I can trust you, man. Okay, here we go. Watch me iterate. I can't do that fancy stuff. All right. So look, that'll do.